Okay, for this video, we're going to be talking about gene mapping, and some things associated with gene mapping, like recombination frequency, the coefficient of coincidence, and the interference. And we're going to, as I kind of go through this video, we're also going to be solving a type of gene linkage problem that's dealing with three different genes. So I have some slides to kind of explain some of these different aspects of gene mapping. Pull it up. So what is gene mapping, right? So gene mapping is the process of determining the location of genes on a chromosome. And so with what I explained today, we're going to be able to find out if you have three genes that are linked on the same chromosome. We're going to be able to find out which gene is in the middle. We're not going to be able to find out their exact order from like left to right, but we're going to be able to find out which one's in the center and the distance between um, the genes next to it to that center gene. And so there's a process to be able to do that. And so what the kind of steps are to start um, is when you're looking at a population that you have, you need to first find the parental phenotypes. And so those are going to be the most common phenotypes. So it's going to be the phenotypes with the largest number in that population. And then you need to find the double crossovers. And so the double crossovers, as we saw the problem, you're going to understand kind of why they're called double crossovers, but they're going to be the least common. And so they're going to be the phenotypes with the smallest numbers. And so you're going to be comparing those parental and the double crossovers to each other to be able to find which gene is switching. So you can find that center gene. And so I'll show you the example that I have here. So I have a population of 1,000 individuals listed here, and the different phenotypes and the amount of individuals with that phenotype in that population. And so on the very left, you can see the pluses, the R's, the S, and the W's. So these are the phenotypes. And so the pluses, they're known to be like the uppercase letters. So the very top one, it says plus plus plus, but it is big R, big S, big W. And that's the wild type. So kind of the most common gene that you would see out in nature. And so for these problems, it's a lot easier to change that wild type, that uppercase to just a plus. It's a lot easier to compare which is switching. And so if you do have a list, like an assignment where they're not that way, I do recommend changing them to pluses, just rewriting those phenotypes. It will make it a little bit easier, and that's what I'm going to be using and explaining in this video is the pluses. And so the first thing that we have to do to find which gene is in the middle, right, is finding those parental phenotypes. So looking at the list of numbers that we have here, which ones have the greatest number in the population, and so you can see that it's going to be the R plus plus, which has 359, and also the plus SW phenotype, which is 351. And so these are going to be our parentals. So I'm going to just put a P next to them for parental. And then we need to find the double crossovers, and that's going to be the ones with the least amount. And so that's going to be this very top one where it's plus plus plus. I'm just going to put a D for double crossover, and then we have RSW, which only has 4. And so now that you found those parental and double crossovers, we need to compare them to each other. And so what I like to do is I'll kind of sandwich the double crossover in between the parental phenotypes so I can compare them. And so I'm just going to write out the parentals here. And then I'm going to put the double crossovers in between them. And so the first one that we have was plus, 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 and then RSW. Okay. And so looking at this first one here, what we're going to be looking at is the difference between the parental and that double crossover. And so seeing our first parental phenotype, we have R++. What changes and what is changing in that double crossover? So we see that the pluses, they stay the same. The wild type stay the same, but that R changes to a wild type, to a plus. So the R is what changes, and the big S and the big W is what's staying the same. And so looking at that second one right below it, we see that that the big R, that plus, the wild type, it stays the same, but the S and the W change. And so you see that the R is the one that is either staying the same or changing out of the two. And if we look at the second one here and we compare them, we see that the R, the little R stays the same, and the pluses, right, they change to S and W. And the lower one, we see that the plus, the wild type changes to the little R, and the S and the W stay the same. So R is the one that's going to be in the middle. It's the one that's either staying the same or it's changing out of the other two. It's the one that's different. And so you can kind of rewrite all your phenotypes to the order to make that R in the middle. We'll need to kind of do that for to look at the next problems in this bigger problem that we're doing. And so R just needs to be in the middle. So it doesn't matter if you write it your phenotypes as SRW or WRS. We don't know the exact order, but we do know that that R is in the middle. And so I'm gonna rewrite some of these. So the first parental, right, is gonna be plus R plus. And then the rest of these that aren't the parental or double crossover, these are all your single crossovers. And so I'm just going to put an S by them, just so we know that, remember that those are all the single crossovers, and we're going to be using them for the next part of the problem. And so this one is going to be SR plus and plus RW, S plus plus, S plus W, plus W. But I didn't rewrite the double crossovers just because we won't really need to do that. We've already compared them to the parental phenotypes, and we won't be doing that comparison for the other part of the problem. So I just did the ones that we kind of need to, which is the parentals and then the single crossovers, which is what we're going to be using. So the next part of the problem that we're going to be finding is what is the distance between S and R, and then the distance between R and W on the chromosome. And so this is called the recombination frequency. So if we go back to the slides here, the recombination frequency is the measure of the likelihood that two genes or genetic markers on a chromosome will be separated from each other during the process of genetic recombination. and this is measured in centimorgans. And so this is probably a new unit of measurement for most people. And so it's just a unit of genetic distance to measure recombination frequency between the two genes on the chromosome. And so you can think of it as that one centimorgan represents 1% chance of recombination between two genes during meiosis. So the distance is a percentage. And so how do we find this recombination frequency or this distance? You take the number of recombinant offspring, and then you're going to divide that by the total number of offspring that you have in that population. And then to get it into centimorgans, because if you just do that, it's going to be in morgans. But most of your teachers or professors who are might have problems or questions like this, instead of having like a decimal, usually your answer will come out into a decimal in morgans. And so if you times it by 100, you'll usually get out that decimal and have maybe a little bit nicer number, but then it'll be in centimorgans. And so we're going to do this to find that distance between S and R and W in our problem. Whiteboard here. And the way I like to do this is to first take the parental phenotypes in the correct order now that we've written them, and then kind of compare them. Okay, so we're trying to find the distance first between S, terrible, S and R. And so that is going to be that change between here and here. And so what I do is I just draw an X right here. And so this is simulating our single crossover. And so going from the top, we'll start here with the plus, and then we're going to cross over to the other one here to the plus and the W. And you see that's just one crossover. Our double crossovers, if you line these up, it would make kind of a V, right? Plus, 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 and that's why it's a double crossover. But this is just a one single crossover. We're only crossing over once. So if we look at our the phenotypes in our population, we'll try and find which one has the plus plus W. And so that's the very bottom one. And then we have 92 individuals that have the S R single crossover right there. And then going the other way, starting at the bottom with the S, and we cross over here, we see it's going to be SR plus. So looking at our phenotypes again, that's going to be where we have 98 individuals. And so, but we need the total recombinant. And so what that means is you also need to account for the double crossovers, because when you do a double crossover, you do cross over in this area between the S and the R. So you also need to add in our double crossovers, which we had 6 and 4 of them, so 10 of them. And then you divide that by the total number in your population, which is 1,000 in this case. And so this is going to give you the recombinant frequency. And so if you put this in your calculator, it's going to come out as 0.2 Morgans. And usually, like I mentioned before, usually you want to times this by 100 for your assignments to get in centimorgans, which then is just going to equal 20 centimorgans. And so that's that distance between S and R. So now we need to do it for R and W. So I'm just gonna erase this here. And we're going to need this initial value, this recombination frequency of 0.2 morgans. So I'm just going to keep this up here so we can use that later. So to find the distance of R and W, we're going to do the exact same thing, but start on the other side, crossing over on the other side. So show you what that looks like. So you're going to make your X here now instead of on the left. And so when we look at this, we're going to start here and kind of cross over. And so written in the way that we've been writing them, is going to be plus RW. So which one has plus RW in our phenotypes? And so this is we have 47 individuals with that phenotype. And now we're going to go the other way, starting up from the top here, going down. So, right, the single crossover in this area. And so that's going to be S plus plus. So which one has S plus plus? We have 43 individuals with S plus plus. And then, like I mentioned again, we are again going to need to account for the double crossovers, which was the 6 and the 4, the 10 individuals, because they also cross in this area. And then divide that by 1,000, the total individuals that we have. And so if you punch that in your calculator, you're going to get 0.1 morgans, or right, times by 100, 10 centimorgans. So now we found that distance between R and W. And so if you have a question where you need to find the total distance between S and W, you just add those together. And so, right, that would either be, 0.3 morgans or 30 centimorgans would be your total distance between the S and the W. And so the next question that you might get for a gene mapping question like this is the coefficient of coincidence. So going back to the slides again, what is the coefficient of coincidence? It's the ratio of observed double crossovers to the expected double crossovers. And how do you find the expected double crossovers? Because we know which ones the observed double crossovers we have, right? There was 10 of them. But to find the expected, you take the distance between, in my slides here, they were using A, B, and C for our gene. So we were using S, R, and W. So this is going to be the distance between S and R in morgans times by the distance of R and W in morgans, and then you times that by the total offspring. And so let's find that. All right, first take your total double crossovers. Then we're going to divide that by 0.2 organs, right? Times by the 0.1. By some individuals. And so if you put this in your calculator, you're going to get 0.5. And so we're also going to use this value for the next question, which is so this is your coefficient of coincidence, or other words, your COC. And so now we can use the coefficient of coincidence to find the interference. And we'll go back to the slides to show what that is. So the interference, it's where a crossover in one region of a chromosome affects the likelihood of a second crossover happening nearby. And it's really easy to find if you already have, right, that coefficient of coincidence. It's just 1 minus the coefficient of coincidence. And so these next bullet points is what's kind of important when you're looking at that value. And so we know our coefficient of coincidence was 0.5. So we just need to do 1 minus 0.5. So it's just 0.5. And so if the coefficient of coincidence is equal to 1, there's going to be no interference, right? Your interference is going to be 0. And so that's not happening in our case with our population here. If the coefficient of coincidence is greater than 1, it's just a negative interference, and this increases the likelihood of the second crossover happening nearby. And so ours is not greater than 1, so it's also not happening in our population. But if the coefficient of coincidence is less than 1, it suggests a positive interference. That's what we have in this population. We have a positive interference, and that reduces the likelihood of a second crossover happening nearby. And so that's how you find that interference. And so, that is kind of everything that you need to know for that kind of problem. It helps with practice. Hopefully this video was able to help you guys a little bit on how to find that gene that's in the middle, and then to find that those distances, that recombination frequency, the coefficient of coincidence, and then, like I mentioned, that interference is not hard to find. It's just the 1 minus the coefficient of coincidence. And so that's the end of the video. You guys have a good one.